Welcome back. We in the last module or last few lectures have discussed on dewetting, and we have seen two aspects. One is the theoretical aspects or the understanding of under what condition a film spontaneously ruptures and dewets. But the other thing that we have seen, and which is pretty interesting, that in this process of spontaneous dewetting of a thin film, you are able to generate some mesoscale structures. So, we have discussed that you just spin coat a thin film, you just heat it up beyond its glass transition temperature or expose it to its solvent vapor, and you see that first the holes appear if the system is unstable, then you see the formation of droplets, and things like that we have already noticed. So, you just start off with a thin film, and eventually this is the late stage, we have seen this video again, you lead to formation of drops. So, this is now interesting because we know that we have discussed a whole lot of things on how topographically patterned or meso patterned surfaces have a lot of industrial application, and the whole science of soft lithography is essentially aimed at that. But here you have a system. The other interesting thing that we had discussed in the previous class is that the periodicity of these structures, the number density of the structures, the size of the structures, they all scale with the film thickness. So, what it implies, I do not have a video or a view graph or micrographs here, but what is important is that if you vary the film thickness, let us say from 20 nanometer to 40 nanometer. So, generically maybe in 20 nanometer you get a array of droplets like this. In contrast, if you take let us say 40 nanometer thick film, you might get some droplets like this. So, this is interesting. So, few things vary. So, lambda varies, number density varies, and the diameter of the features, let us say, vary. Okay. So, here if you now compare with soft lithography and you wanted to sort of create different structures, let us say. So, the only way of doing that would have been to have different stamps with different features. But here you see that you have additional handles or to sort of tailor the periodicity, size, number density of the structures. We also talked briefly in the last class about bilayered dewetting, where we talked about the reduced interfacial tension. So, that also affects the number density as well as the feature size, right. So, in a way this spontaneous instability or instability mediated techniques sort of give you an additional handle or tuning parameters based on which you can create different structures without any hardware requirement. So, the key advantage would be that you have these smaller droplets versus the larger droplets. You do not need any additional hardware like a stamp or whatever, you just vary the film thickness and you get to that. The second major advantage is that if you look at this evolution sequence, this evolution sequence continues till the very end because you have kept the temperature beyond the glass transition temperature, it is elevated at glass transition temperature. But let us say I decide that okay, I do not want my film to dewet completely, and I let us say want a holy template. So, I want a film which has some holes, what I would like to want to grow something, let us say. I have the advantage of stopping this process right here, and how does one do that? By simply quenching it, or in other words, I heat up the film based on its thermodynamics, it is now evolving, and now I reduce the temperature at an intermediate stage. I do not go all the way up to complete dewetting. So, I have the advantage of stopping the process at any juncture and thereby create different structures. So, let us say from the same thin film now of let us say 40 nanometer or 30 nanometer thickness, we can have holes, we can have ribbons, we can have droplets, and all these things are possible. So, that way the film dewetting or spontaneous dewetting, which is extremely unwanted. We also discussed this particular aspect, which is unwanted from the standpoint of a coating application, can really find interesting or can really be used in an innovative way to generate surface patterns with meso and nanoscale lateral dimension and resolution. What is the real problem? The real problem is that these structures, whatever structures, the instability mediated structures or patterns that what we get, they are highly random, they are isotropic. Structures. So, this is a severe hindrance and significantly hinders any major practical application of instability mediated techniques being used as a viable patterning method. So, that is a real problem. What are the advantages? Advantages are the evolution controlled at an intermediate stage. So, many structures can be obtained either by varying the initial condition or by initial conditions or by varying the physical parameters. I will give an example of that, that will make it clear, or the extent by controlling the extent of this propagation or progress extent of dewetting. So, initial condition, you understand whether I take a 20 nanometer film or a 40 nanometer film, that is by controlling the initial condition. By varying physical parameters, well, you can tailor the surface tension by sort of submerging the film under another liquid layer or another polymer, or you can even do things like you can tailor the surface energy of the substrate, because yesterday we talked about the fact that if your holes are growing and the surface is extremely non-wettable, there is a chance that there might be rim instabilities which are occurring. In contrast, if the wettability is not that low, the one would typically get a nice neat retraction. So, that itself sort of even for the same system, you can lead to the ribbon like stage vis-a-vis a completely random array of droplets. However, still the major disadvantage that remains is that these structures are random. So, in order to sort of use them as with any viable application, the most important requirement, major requirement would be to align these structures. This is the key requirement, and therefore, in recent past significant focus is on, the significant research is going on in these directions to work out strategies which can be used to align these structures, both with simple polymers like polystyrene, polymethyl methacrylate, which are good model systems, as well as for functional polymers. So, we will discuss some of these approaches and pick up some examples to give you an idea how it works. So, the easiest way to sort of achieve it is based on using some templates or which can guide the evolution pathway. And the templates that are most commonly used are nothing but topographically or chemically patterned substrates. We will give you some examples from that. But if you remember, in one of our very initial slides, we talked about 3 paradigms of mesoscale fabrication, right. One of them was self-assembly based techniques, one of them was the top-down techniques like the lithographies, and the third one we talked about another form of a bottom-up approach is the self-organization. So, this majority of this instability mediated patterning methods, we have argued that they are essentially self-organization. Now, whenever you are using a template, it is essentially a combination of the top-down methods and the self-organization methods. Okay. So, why top-down? Because you have to make your topographically or chemically patterned substrate by some lithography. So, if you are talking about a chemical patterning, you are going to use, let us say, a technique like microcontact printing, which is typically used. If you are talking about topographically patterned surface, you can use photolithography or some other soft lithography methods. Okay. So, we will see how it works, but interestingly there is a possibility of aligning these duetted structures was first shown by Jones, famous scientist from UK in around 2000, and the paper was published in Nature, where they simply took a glass slide and before coating it with a polystyrene or a PMMA film, all they did was to rub the glass slide in one particular direction with some emery paper. So, this rubbing essentially resulted in some scratches, micro scratches on the surface of the glass slide, and eventually when a film was cast on this particular surface and the film was allowed to duet, the strong anisotropy resulting from this rubbing or scratching in a particular direction made the structures which were completely aligned. So, that was the first time which you can see here that the structures. So, this is the typical structures you would get from a duetting of a spinodal duetting, the early stages of spinodal duetting on a flat surface. But instead of using a flat substrate, the same substrate, if you just take a micro scratched or a rubbed surface in a particular direction, you can see that the structures are highly aligned, and you can also verify the isotropy of the surfaces here from these FFTs, fast Fourier transform diagrams. Okay. So, this was a conceptual approach to show that yes, indeed it becomes possible to align these structures, but you have to understand that by using a technique like rubbing, for example, it is not going to work for an industrial application or for producing something in a reproducible manner. So, what has been a major approach is essentially to duet on a topographically or a chemically patterned surface. So, let us first talk about a chemically patterned surface. You all understand what is a chemically patterned surface. So, it is something like this. So, let us say these are domains with gamma 1 and these are domains with gamma 2, and gamma 1 is less than gamma 2. So, gamma 1, these are less wettable domains. So, what happens is when you are talking about dewetting on a chemically or a topographically patterned surface, your equation, which the thin film equation, if you remember from our 35th lecture, which has this form, gets slightly modified as okay, I will write it like this. I'll rewrite it. So, if you compare this with this form of the equation, you first see that H has been replaced with H minus AF, where F is a or Z equal to AF x y describes a rough substrate, and the effective film thickness now becomes so for a smooth surface you can write that A is equal to 0 for a smooth surface, okay, or phi is equal to eta is equal to H for a smooth surface. So, this is a modification that comes in. So, firstly this parameter sort of takes care of any topographic roughness that is present in the system. But more importantly, what happens is phi now becomes, earlier phi we had taken to be a function of H only, okay. But in this case what happens is phi becomes a function of x and H. Therefore, this term phi x now becomes, which was this we had while doing the linear stability analysis, we have used phi x as del phi del H into del H del x, but now there is an additional term present in this, which is del phi del x evaluated at any specific H, or in other words this particular term represents the second term is the force due to, or is due to the variation in potential, the in-plane variation of potential due to chemical or and physical heterogeneity. So, in other words, under the action of this particular force, the fluid sort of moves from the less wettable area. So, this is sort of an in-plane potential gradient. So, earlier what we have seen that for a flat film on a homogeneous surface or a smooth surface, it was the sign of this term, which essentially if you consider the van der Waals force, you can write this in terms of the Hamarkar constant, and then we talked about this term in terms of the sign of the Hamarkar constant. But here additionally, even if the Hamarkar constant is positive or negative, or even if Hamarkar constant sort of is giving you a stability, this additional force field arises due to the in-plane gradient in the potential. So, what happens is, due to the in-plane potential gradient in the potential, now if you have a thin film on a chemically patterned surface, let us say, what is going to happen? So, these are domains which are non-wettable. Okay. So, the film will preferentially rupture over these areas. So, in simple terms, what will happen is that, suppose if you have a flat surface vis-a-vis a chemically patterned surface, and you have a film over here and you have a film over here, same thickness, let us say, here the evolution or the dynamics is completely random. In contrast, what is going to happen, the likely scenario is that the film is going to rupture only over these locations, and the remaining part of the polymer will retract to the areas having gamma 2. So, you will be the morphological evolution, instead of being a completely random evolution, you will get isolated strips of polymer like this, or in other words, these are the zones with gamma 1, let us say, where the film has ruptured and the polymer has, the meniscus has retracted back over the areas with thickness where with surface energy gamma 2. Okay. So, this way, instead of a completely random pathway, or in other words, what it means that here on the surface the holes can appear at any random location. In contrast, over here you are since you have these zones which have lower wettability. So, the lower wettability zones act as preferred centers for rupture of the film, and therefore, the final resulting structures becomes strongly anisotropic. Okay. So, this is how it goes on a chemically patterned surface, and you can use a chemically patterned surface to align the structures. Of course, what is important that other parameters also come into play. So, suppose this is a chemically patterned surface, let us say I put the markers here. Okay. So, gamma 2 let us say is less wettable, or gamma 2 is more wettable, I am sorry. That is how we have drawn the picture. Gamma 1 is less wettable. So, these are the domains with gamma 1, let us say. Film has ruptured and it has now got accumulated over these zones. Okay. So, now other parameters will also come into play. Let us say the width of this zone. So, let us say these zones have a width of L1, these zones have a width of L2. So, the width of L1, the relative width L1, L2, the periodicity of the structures everything becomes important. Because what you have to understand that after they have duetted, they now form actually very long polymer threads. So, there is always a tendency of Rayleigh instability being exhibited. So, this was shown in a 2002 paper by Alamgir Karim's group, that depending on the width of the less wettable and the more wettable zones, you can get a whole lot of structures. So, let us say for very thin threads, I mean if these zones are about a micron wide, your structure will comprise isolated polymer ribbons. Okay. But in contrast, if you have wide rings, let us say few micron, then you might have aligned droplet arrays. Okay. Like this. For even wider, so let us say this is L1 1, this is L1 2, for L1 3, even wider zones, you might have a double periodic array of droplets. So, once you now confine the entire polymer film to one of these zones, okay. So, now again it is a question of it's now a localized isolated thin strip of a film, okay, thin strip of a thin film. So, now again it can show its it can rupture following its spinodal mechanism, or it can exhibit in-plane Rayleigh instability or whatever. But you can see that as compared to, for example, if you look at this particular figure, you can see that you again have droplets which are common in Dewetting, but these droplets are no longer completely random, but they are pretty well aligned. So, this can be easily accomplished with microcontact printed surfaces. One can also sort of tailor the extent of wettability contrast. So, that is another very interesting work that was published by the same group, but few years back. So, you have a microcontact printed surface. So, we all know this is what is a microcontact printed surface. So, let us say this is gamma 1 and gamma 2. So, they also showed that depending on the difference of or the extent of ordering is a strong function of this difference. Because how does it manifest in the equation? Because the strength of this particular term actually depends on the relative difference. So, if you take surfaces, different surfaces where let us say the gamma 1 minus gamma 2 is varied, and this can be easily done by from your soft lithography understanding, you can immediately say that if you sort of take silents which have different surface energies, or take a base surface which has different surface energy, this can be accomplished. So, lower is the difference between gamma 1 and gamma 2, what is going to happen is that the strength of this term is going to become weaker, and the anisotropy of the structure sort of reduce, or in other words the extent of alignment sort of gradually reduces, and the structure tend to become more random. In fact, they could show that there exists a critical value of delta gamma, that is the in-plane wettability gradient, below which the ordering is completely lost. So, again these are very advanced areas in which research is still active, lot of new findings coming every year. But so, from completely random structures to this type of aligned structures. So, this is exciting now, because again here you have the potential to stop the evolution at any intermediate location, and also what we find that the final morphology depends on a commensuration of a whole lot of parameters. So, film thickness brings in the natural length scale of instability. So, lambda is the natural instability length scale, which corresponds to, let me remind that if you do the analysis for a particular thickness on a flat surface, do the linear stability analysis, what you get from the fastest growing mode. So, that gives you lambda. So, this is the natural instability length scale, which is a function of the film thickness, the H0, and here you have another parameter, that is the lambda p, which is the periodicity of the patterns. So, the final structure, final morphology of the structure is a strong function of the commensuration between lambda and lambda p. Okay. So, of course, apart from lambda p, issues like LP, delta gamma. So, let us write it down neatly. So, on a chemically patterned substrate, the final morphology becomes a function of lambda, which is a function of the film thickness, lambda p, LP, delta gamma, etc. And therefore, again you have whole lot of handle by simply using the same template or same pattern substrate, but films of different thicknesses, you can get to different structures. You can you can use same pattern substrate, but with different delta gamma, you can get to different structures. So, these are the advantages. Unlike top down soft lithography, where every time you want to create a new structure, you have to have a different stamp. So, you can really rule that out and work with tailor or play with around with the parameters, and you can get to a whole lot of things. But the critical thing is that this dependence is often nonlinear. It is a multi-parameter dependence and it is often nonlinear. So, if you want to sort of do experiments blindly, you might not lead anywhere, because every new combination will give you a completely new set of results, because the initial conditions are extremely important. So, in that case it is very difficult to draw some cohesive understanding only based on experiments, unless the experiments are sort of very well planned. So, what typically is found is necessary is to have a very strong and robust simulation tools. There has been lot of work from IIT Kanpur group and other groups also in the world on simulation of these type of system, which really sort of become very handy in understanding the or predicting the likely morphology. So, if you have a robust simulation tool, then you can sort of identify the structure you want to obtain and do experiments based on picking up appropriate initial condition. That reduces your experimental efforts to a large extent. So, similar to using a chemically patterned surface, one can also use a topographically patterned surface. For aligning the structures. So, we all understand what is a topographically patterned substrate. So, it is something like this. So, in principle what will happen the moment you use a topographically patterned substrate, it is this particular term that becomes very important. So, now the film thickness sort of varies, theoretically the film thickness varies along the length. So, h itself or eta becomes a strong function of x, but in practice it is more critical, because how do you really get a film on that, on this type of a surface? Because on a flat surface what you do is, this is your flat surface and you simply spin coat, you get a film. How do you get a film on this type of a surface? Because if you spin coat, we have talked about it very briefly, and here you can see again that by directly spin coating on a on a topographically patterned substrate, it is possible a continuous film only above a critical solution concentration for a, of course, you have to understand that this concentration is nothing like a universal gas constant or something like that, this critical concentration for a specific geometry of the substrate and wettability. So, how wettable your substrate is, and this wettability is not the water contact angle or whatever, this wettability is governed by the wettability of the substrate by the coating solvent. Okay. So, this is very, very important. Immediately you can understand, if you have a more wettable surface, the critical solution concentration will be low. If the surface is non wettable, it will be high. So, here you can see a whole lot of things. So, this is this particular experiment was done in our lab. So, this is the topographically patterned substrate, it is a grating pattern substrate that was taken, which was lithographically fabricated. So, now if you try to spin coat only above a critical concentration, there is no point in quoting the number because that varies from case to case. Let us say Cn star, we could get a continuous film. So, let us say Cn is the concentration of the dispensed solution. So, only for Cn greater than Cn star we could get a continuous film. And the other important thing is that though you get a continuous film, even in a continuous film, the surface of the film is not smooth. Okay. And in fact, what we get the morphology, this we have very briefly talked, the morphology of a continuous film on a topographically patterned substrate depends largely on the wettability of the substrate. So, we have talked and we have shown recently in this paper that the structures will look like this. So, you will have a film with an undulating top surface and the undulations will be in phase with the substrate patterns only when it is completely wettable, the substrate is completely wettable. In contrast, the structures or the undulations will be out of phase if the substrate is partially wettable. So, this is a very recent and exciting finding. So, for a system like this, what will happen, even if you have a continuous film, you can immediately understand that there is a periodic spatial variation of the feature height, of the film height or film thickness. So, if they are out of phase, you can immediately see that these are the locations above the above the substrate protrusions, the film thickness is much lower. So, the surface undulation. So, again irrespective of this morphology, the surface fluctuations we have talked about the surface are present. So, here the chances of the surface fluctuations growing and touching the base of the substrate, which is here, is much higher. So, one would expect a preferential dewetting to be rupturing on top of the substrate pillars in this type of a case, which is very common, and immediately add sort of a directionality to the dewetted structures. But more interesting is even for Cn less than Cn star, you will not get a continuous film. So, because there is not adequate polymer, or there is, what happens is there is actually an in situ dewetting during the spin coating process itself, and under certain specific conditions you might get some random structures. So, let us say this is a random structure. I am not going into the detailed mechanism. If anyone is interested, you can contact me, or these are random structures. But here you see some structures like these are isolated droplets already, what you might be expecting to get by dewetting, or these are thin strips of polymer within these grooves of the substrate. Okay, so, these are pretty regular structures, and you can also see that this thin strip already exhibits a Rayleigh instability, which is seen in this inset. So, what you do not get is for Cn less than Cn star, you already get some structures which are resulting from an in situ dewetting. So, the discontinuous structures resulting from dewetting during spin coating, from in situ dewetting during spin coating, and this is what is known as spin dewetting. So, one critical question is that how does one really look at a film which has an uniform film thickness on a topographically patterned surface? Is it possible to do that? Film with uniform thickness on a topographically patterned substrate, because if you spin coat directly, it is obvious that you will get a film with an undulating top surface, and this was a pretty challenging problem. But what is typically done in this case, a very complicated, rather complicated, but pretty well known experimental protocol is used, which is based on floating of a thin film on a liquid surface, let us say an inert liquid surface like water. So, what is done, a polystyrene or any polymer film is first spin coated on a flat surface, and then it is peeled off from the from that surface by floating on water. So, this is a very complex, not a very complex, but it is a very tricky experimental protocol where you sort of hold through the edge and the film sort of detaches completely from the substrate in which you have coated it. So, you now have a freely floating film on the surface of this liquid, and which you have to recapture now with a topographically patterned substrate. So, this is difficult, but it can be done. And while doing this, following this protocol, so this has been done for a lot of systems even before, but while we were capturing this with a topographically patterned substrate, it was also realized that depending on how this capturing step or this step is implemented, you can have different morphologies. So, for example, if you have a rapid horizontal liftoff from water surface, you get to a morphology like this. Where it is similar to this, where a film is like a stretched sheet on the topographically patterned substrate, which is touching only the top of the substrate protrusions or the substrate top of the stripes if it is a grating. In contrast, if you have a slow vertical lift off from the water surface, then you have this type of a conformation which we term as conformal adhesion, where the film is conformally adhering to the substrate. Depending on if you have pull it out at an angle or something like that, you can have an intermediate configuration. So, now this type of a system, how it is unique and distinct from this type of a system, here the film thickness was a function of x, but here you have the potential of having a film with uniform thickness on a topographically patterned substrate. And what was important to realize that this initial adhesion, whether you have a focal adhesion or conformal adhesion, so because of the presence of this substrate or the template, the structures anyway get aligned, what you can see from this picture or this picture, that the structures are aligned. But what is most interesting to notice is that if you have initial focal adhesion, the structures go and rest on the top of the stripe. In contrast, if you have conformal adhesion, the structures go and sit within the valleys. So, here now you have an additional handle on tailoring or controlling the positioning of the droplets. If you go on taking narrower stripes or gratings with reduced periodicity, you can show that the periodicity of the structures can also be controlled. You can get smaller droplets, they can get aligned, you can sort of reduce their periodicity in comparison to their natural periodicity by at least 1 or 2 orders. If you take a more complex template like this with a 2D ordered array of square pillars and make a sample exactly following the same route, with the conformal adhesion, you can have some very nicely arranged Dewetted droplets. You see, so this is the original template, and you see by Dewetting of this film, what has happened is that at each of the interstitial location between the channels. So, here was the structure. This is an array of square pillars onto which you have floated your film and then allowed it to duet. So, what you see that at every interstitial location gets filled up with one Dewetted droplet. Okay. So, the periodicity of the droplets here is completely governed by the periodicity of the template, right. So, you can take templates with different periodicities and you can now tailor the periodicity, the size of the droplets. The size of the droplet also is a function of the size available within. So, scientifically it is intriguing because with a 2D ordered template, perfect templating where every location gets filled up by a droplet of equal size or the maximum possible size that can be accommodated, is possible for a specific thickness, which again is not a very critical, very important number, but one needs to understand that there is a critical thickness for a specific template design. These can be resolved with simulations, and people have been doing about these sort of things. So, for larger or smaller or lower or higher film thickness, the ordering sort of tends to get distorted. As you can see, you have some droplets which are missing here, you have droplets which are smaller, or here you have some droplets which are interconnected. In contrast, even on this template with this 2D order or this array of square pillars, if you now have a focal adhesion where the film is just touching only the top of the asperities or the top of the protrusions, you can again see that the droplets now go and align themselves on top of the pillars. So, this is a image which is a nice image. I like this image a lot because it had a zone where it had some defect. So, here you can see through this defect, through this zone, the bottom of you can see clearly the substrate structures, and these brighter spots which appear are essentially because the Dewetted droplets now have gone and settled on top of each of pillars. So, this way by controlling the extent of initial adhesion, it becomes possible to finally control or further control the positioning of the droplets. So, this is nice case study. This is another interesting case study, and I will show you a video which will excite you more. So, you had a template like this, a holy template. So, you had a surface with holes and a film was floated on that. So, you can see through this AFM image that this is a film, intact film, which is floated on this particular templated zone. And if you now allow the film to duet, it is more like a focal adhesion. So, what happens is in a focal adhesion, this is the film. So, over these zones, the energy penalty of sustaining two separate film air interfaces is higher as compared to these zones, and therefore, it is sort of a freestanding film over these zones, and they rupture rather explosively. So, this has been what is the theory says, but and therefore, you expect that the film will rupture over these zones in this particular case. And look at this particular video. So, this is what you see, a film has been floated on this type of a surface, and if you now look at the video, you see that some flash bulbs are going off somewhere. Okay. So, let me just tell you once more. So, here you see some bright holes on which the film is still intact, which has not ruptured, and these brown colored holes are the zones over which the film has already ruptured. So, if I allow to run this video again, you see that at some of these brighter holes are sort of getting darker. So, that is what is happening is that the film is sort of rather explosively rupturing over these zones. Okay. So, you can clearly see that the film is dewetting, it is rupturing over those zones, and finally, once it ruptures. So, this is the intermediate morphology. So, you have a possibility of stopping the evolution sequence right here without allowing any further progress. So, you can get a film which is also holy, and then you can transfer that film or use that as a membrane or whatever. But if you allow the film to duet further, it forms again droplets which corresponds to the lowest energy configuration or something like that. So, here is the video. If you want to see, have a look at it again. So, you see that some of the films are the intact portions of the films over the which are freely hanging over the holes, they are sort of rupturing and opening up, forming a morphology like this. So, the other interesting thing is that if you have a film which is in conformal contact, but which is much thicker. Okay. So, it is something like this, the film is much thicker as compared to substrate, there might be some mild undulations. This is a floated film, so there is no question of film thickness varying. So, what happens is that in this particular case, in this particular case, the film does not rupture at the length scale of each of the pattern feature. So, what happened, what we showed in the case of this movie, for example, is that the film ruptures at the length scale at the level of each feature. Okay. So, you have an array of holes, and you have a film which is floated on that. So, the film ruptures over each of the features, and then the subsequent morphological reorganization takes place. And that is the same thing we have noticed here. We have argued here that the film ruptures over each of these zones over here, or even for a chemically patterned surface, the same argument that we place, that over each non-wettable zone the film ruptures. But for a slightly thicker film, it is more interesting in the sense that the film does not rupture at each of these at the level of each feature. In contrast, it sort of ruptures with the formation of holes which are non-correlated to the substrate or the template, like you see the formation of random holes on a topographic on a featureless flat surface. Okay. So, you see these holes under an optical microscope, pretty high resolution optical microscope, and you see, so this is on a surface comprising these square pillars or whatever. you see that you can see the bare substrate also. But if you examine it, so this is what you see under an optical microscope. Okay, so the hole has opened up. You can also very clearly see the formation of a rim. But if you examine it under an atomic force microscope, you see that as the rim retracts, so this is the hole has opened, this is the direction of the retraction of the rim. As the rim has opened up, it sort of, while retracting back, it leaves behind a droplet at each of these interstitial location. So, your final morphology, if you allow complete dewetting, has structures at 2 length scales. So, if you see a low magnification image, you see some random droplets which sort of resembles very the dewetting on a flat surface. If you examine with a higher magnification image, what you can see that, well, these droplets are not resting on a flat surface, but they are actually resting on a topographically patterned surface. And if you investigate each of these zones, you again see a structure where you have tiny droplets which are occupying each interstitial location like this. So, for a thicker film, you actually are able to generate a multi-length scale structure by dewetting on this type of a surface. There are many more case studies which are available. I just picked up one case study to impress upon you that in combination with suitable templating strategies, which in this case is use of a topographically patterned or a chemically patterned surface, it becomes possible to align the dewetted structures. And there, let me tell you that there has been significant work in this area to use these type of structures for commercial application. For example, this type of a structure with a functional material, each one can sort of be used as a pixel for a display or some other application like that. So, they have been used in various types of application like microelectronics, plastic organic electronics, even in biotechnology and things like that. So, this class I gave you a glimpse of how a template guided self organization or dewetting, let us say to be more precise, on a chemically or a pattern topographically patterned surface can be used to align or impose some directionality or anisotropy to the otherwise random and isotropic dewetted structures. Thank you.